almost forget about that. Right. So just like a TLC plate, our column separates the compounds relative to their polarity. And it's basically the inverse of a TLC plate, where instead of we are going from a polar compound to a more nonpolar compound, it's going from nonpolar, the polar is at the top, and whatever that's down is nonpolar. And as the mobile phase is traveling through ours, there will be a separation. Sorry. The compounds will separate, and there's a relationship between the stationary phase and the mobile phase. And then we collect the fractions. And this is just a chart you guys can reference to with the alkyl chains and the double bonds of alkyl chains being the most nonpolar. And then we move to ester. Oh, sorry. They all are grouped. And then here's our ester. And then this ketone and aldehyde, and so on, with the acid being the most polar. We don't use water in our system because it would dissolve the silica gel. So we don't want that. Yeah, the drawing is not synced. I have to use the one in the presentation. And here's just a little practice. And I've give you guys 2 minutes to sort this out. Which one is the most polar, which one is the nonpolar, and which will elute out first.
Maybe that's why.
Anyone got an answer to that? A. So for A, let's see, we have two, sorry. So we have two ester groups. And here we have two acid, which is the most I assume that is the most polar. And this might change as we move on. Here we also got two ester, but the format here is in trans. And this is one ester and one acid. And sorry, ester, acid. And just by our previous trend, we know that this is the most nonpolar. This is the most polar. And the one we have for C is trans. This is actually more or less interactive, but yeah. On the column, we will have the most nonpolar compound that's coming down, and the polar compounds will stay up here. So we can immediately cross A and B and C, B and D out. And this only leaves us with A and C. And to determine which one is more nonpolar, we can kind of see that there's a hydrogen. There's a hydrogen. There's some sorts of interactions going on here. So that's why it's more or less more polar than A. And this is from 2016. Sorry, it's C. My bad. Usually, based on the answer in the chat, it's not usually the case because, how should I say this? Actually, I'm not too sure about this one. Sorry, guys. So far, I can only exclude that it's not B and D. But for A and C, it deals with the why is trans more nonpolar. Than cis. Okay, I agree. Trans is more stable than cis, and therefore the intermolecular reaction, the stabilization is more. That's why it's more nonpolar. Yeah, right. Trans is more nonpolar. And this is one of the slides in the lecture. And what Dr. Rutte explained before is that first of all, it takes around so we have R of 0.2, and this will give us 5. This means that if this is our volume, it takes 5 times of the volume to get the spot down to the out of the column. And this is just an estimate. And he also noted that in order for a good separation in the column, the difference between the spot and the next spot, we're not interested in the one on the top, mainly the one we have and the one that's below. The change in RF should be around 0.2 to 0.3. Anything that's less than that or higher than that would be considered not a good separation, just based on the criteria that was listed in this course. Oh, 5. 1 divided by point. So let me get this out. It's just math. 1 over 0.2. That's the RF value, and that's just 5. And the volume is the volume of the column. So 5 times the volume to get this spot out. And suppose this one is 0.7. Oh, sorry, this one is 0.7 RF. And once you get the calculation down, it should somewhere around 1, I believe. Yeah. So that's 1.42. And times the volume, it will take around like 1.5 of the volume of the silica gel to get this out. And then we have a question from the dear kids. And you guys can work this through. Yes, Nina. Yep. It's B. And maybe annotates. It is B. because we have a change in RF of 0.2. This one is too large, it's 0.6. This one's 0.1, too small. And 0.4 is too big. Everybody got that?
Wait, this might be a stupid question, but isn't going from the RF of 1 to an RF of 0.07 or 0.7 only 0.3 difference? For A?
R of 1, oh, sorry, yeah. So R of 1,
why would that be wrong?
because if the RF is 1, this, based on the previous knowledge, we can confirm that there's one spot, it might be 2 or 3, that all stack on top of each other.
Oh, okay. Okay, thank you.
Yeah, that's why.
Can you repeat that? I missed that.
Okay. So for a good separation of the TLC of the column, the spot we have on the TLC plates and their relative RF values. Suppose this is 0.3 and this is 0.1. We want the difference in the RF value to be around 0.2 to 0.3, around this area, and this sits at 0.2, so it's acceptable. So when you create the column, the separation will be good enough that there's enough separation and they won't stack or mix with one another. If the RF is too big, like this one is 0.4, it will take more volume to get the stuff out. And so if it's 0.3, that will be that will use less volume than the one if you use 1/4 or 1/0.4. It's just a idea of being resourceful. So that's why I want to use less to produce the same results.
How do you distinguish between A and B in this question?
Yeah, and 0.1 is less than 0.2, so that's not acceptable.
I mean, between 0.3 and 0.2.
You mean C? The difference here is
A versus B. A is 0.3 and B is 0.2.
Okay, yeah, right. So A, the RF is 1, and that one is all the way on the top. This means that you can have multiple spots on it instead of just one. So okay. You can have 2 or 3 compounds.
So if RF is 1, it stays. That means it stays at the top.
Yeah, and we don't want to create a plate that has a RF value of 1. It's not meaningful to analyze it, unless, yeah. Besides, you know that it's really polar or really non-polar, according to the mobile phase, and then fix it. Here's the next question. This time they didn't give out what's the RF value of each spots, and just by judge of an eye. And the first thing I saw is that D is not the answer choice because that one is way too up. There might be stacking spots, which is not good for isolating and purify it. And the question asks the mixture of the isolating purified in the middle spot. So we want to separate the middle spots, which is this, and this, and that. What do you guys think? Which one seems more promising? Which one seems more promising? Yep. I have to agree with the people who say B, because for C, suppose this is 1 centimeter. That one says I somewhere in the middle, so RF of 0.5, and that one RF is around 0.1. The difference is greater than 0.2 and 0.3. This one is RF is the RF is 0 and this one is like 0.2. And that one is just too close. These two are too big. And this one is just right.
Also, did you say on D the problem was it stayed at the top?
Yeah, right. It's way too up, way too far up. Usually we want a plate that looks kind of like the highest R value should be at around 0.7. That's the highest. Or maybe somewhere lower, like 0.5 or 0.6. But if it stays or is really close to the solvent front line, then the quality won't be that good. And it's won't be accepted to perform separation on the column. So the takeaway is this is the golden ratio you guys want to remember. Just sit around that range and you'll be fine.
Sorry, can you repeat one more time what you said about the spot being on the solvent front line?
Mm-hmm. So assume that I chose this mobile phase to be a very polar solvent, like 1 DCM to 4 methanol. If I chose a more nonpolar solvent, like 1 to 1 DCM to 1 methanol, the spots will get bring down, right? And what's gonna happen, perhaps this might happen because there might be another spot instead of 3. Because if the spots travel too quickly, eventually what might happen is that the 2 spots will get stacked onto one another. So that's just a source of error.
Okay, thank you.
Mm-hmm. Hope you guys get that. And then the next one. So we have a question about the advantage for purifying organic compounds using column, crystallization, and distillation. So instead of thinking about column chromatography, we have to think about what we are manipulating with crystallization. So first, we know that in crystallization, we have to dissolve the compound from solid to liquid, and then we have to also cool it down. So which means we have a transition between solid phase and liquid phase. For compounds that remain solid, it's fine to do crystallization. But if our compound cannot crystallize or it cannot remain solid in the temperature we want, then we cannot carry out crystallization. And distillation can only work with liquids. We cannot distill solids unless you can amp the temperature all the way up. To just basically melt the solids. But usually we cannot carry it, and it's really hard to do. But for column chromatography, we, regardless of what you have, like you have some solids or liquids, the solids can be dissolved in our your solvents and then just pass through the column while they remain liquid. If it's liquid, then it's even better because they can just travel through the silica gel. Okay, so for distillation, Distillation can only carry out purification on only liquids. It happens that if the system you chose, the solids remains undissolved and it cannot go to transfer into gas phase, then it cannot go through and you cannot separate that. But that's not a problem for column, because once you chose the solvents that can dissolve your solids and liquid, the liquid just goes down. Once the solids can be dissolved, everything dissolves, and then you can just pass through the column, and then you can collect it. But for distillation, usually, and for most of the case, it's true that you can only separate liquids instead of solids. So crystallization is just solid only. And distillation is liquid only. And column is both. And then we can move to the next one. So the question asks that the column and TLC plate separates compounds in the same way. Yes, because they will separate depending on the direct interactions between the stationary phase and the mobile phase. And now we have to compare that. What is the advantages of column and TLC? TLC is limited by their physical dimensions. It's just one single sheet of plate, and you can only spot one single spot. And for column, as Professor Rudick noted in the lecture, it can be the column can be a pipette, or super long, like a 20 liter tower, as a column, which is used in the industry. Yeah. Chemistry people, they like to make big stuff. And TLC, so the TLC is limited by a dimension with a width of very low. And the spots and the compounds can only be spotted in a limited amount. You cannot spot too much, otherwise the plate will be poorly developed, because the compounds will be very concentrated and the separation will be good. And remember, column is a technique that can be used for purification, and TLC is mainly to use analysis. So can anyone tell me what one of the advantage of using the column?
Well, you separate what you get out what you want, basically, where you can separate them and then you can collect what you want at the end.
Mm-hmm.
And
Yes.
whereas in TLC, it's just separating it.
Mm-hmm. Yeah, pretty much. We got it. This one is used to collect, the column is used to separate the compounds and you collect it. And TLC is just more of a visual representation of what was your composition in your solution. And for 15, what evidence in the TLC experiment will indicate that the sample is not clear? So TLC plates. We have two. Move this over. And we pass it through a mobile phase. Which was clear, 1 or 2? Yeah, 2. It is 2 because there's only one compound. And for 1, there's 2 compounds, which means there's impurities. It's not pure. So that's the explanation. Gas chromatography, that will go to lecture 9, which will be the lecture later, but I can explain it right now. Yeah, Mackenzie got it. So, earning that, like you are comparing gas GC compared to TLC or GC compared to column. GC compared to column, okay. So one of the nice things about gas chromatography is that you can see exactly what was the composition of each compound to an exact value, like percent of compound based on the area you have. And GC is more or less of a analytical technique. And column is a preparative technique. Column. Preparative.
What do you mean by preparative exactly?
To set, like you're preparing an experiment and you want to separate the compounds, basically obtain your product.
Okay, so you obtain one of the products, that's why it's preparative. Okay.
Yes. Sorry, I'm drawing with my mouse, not a pen. So yeah.
Isn't it just qualitative?
Yeah, that one's qualitative. GC is qualitative. Quantitative.
Yeah, but column would be qualitative.
Yes. Yep. And that's. And did I answer your question, Nita? Okay. And that basically sums up the entire discussion on column chromatography. And if you guys have any questions, please let me know.
Well, TLC is analytical only too, right?
Yeah, right.